All right, this is going to be fun. It's going to be a lot, but it'll be fun. I'm Corbett. I will be serving as the moderator or commentator on the session that I'm about to show you, which is PhD level chemists presenting for each other. Normal people were not in the room when this happened, and they were not the intended audience, which is why I am here to help kind of translate some of the stuff. My process here for all of these 31 weeks that we're continuing with on this Chemistry of Indoor Environments project is to have a conversation with the researcher who is presenting. I ask them a bunch of questions because I've seen their presentation at least 3 times. And I'm like, okay, well, here are the things that I don't understand. And at that point, they answer my questions. I make notes on things that I think are pertinent to the conversation about the science of homes so that we can have practical, actionable advice to be able to use from these amazing experiments that they've done. So quickly, this session is by Barb Turpin, who is an awesome person. She was in season 3 of Home Diagnosis, our television series on PBS. You can binge watch that entire season now online at homediagnosis.tv, and also you can see it on PBS, obviously. And she's talking about water films. So water films, super important. It turns out you'll see why. The tools, and I'm going to try and like make these obvious to you before we start every session. First, a hygrometer. This is a data logger. So this is a temperature, relative humidity sensor. And what this specific kind of sensor called a data logger does is keep track of it so that you can see a graph over time. This is one of the tools that they would be using in this bunch of experiments that she's about to talk about. You also need to be able to see the temperature of surfaces, and that's why you might want an infrared camera. And this one happens to have a moisture meter on the back for surface moisture content. And that's nice, but you also want to be able to poke holes in things and see what the moisture content below the surface is. And that's why you have something like this. Don't go around poking holes in your clients' houses, like go behind pictures or in closets, places where they're not going to care. So those, I think, would be the important tools to begin with so that we know how we might be able to replicate some of the things that Barbara's about to talk about. Enough said for me. Let's begin.
Good morning. I'm going to talk about water-soluble gases, and their relationship to buildings. So water-soluble gas concentrations are elevated indoors. I think you saw this slide on the graph on the left already. It shows water-soluble organic carbon concentrations inside 13 homes collected with a mist chamber. And yeah, the water-soluble organic carbon concentrations are 10 to 20 times the concentrations we see outdoors. On the right is mass balance on WSOC done in the CASA field campaign. And we can account for in that home more than half of the WSOC with small organic acids, carbonyl compounds, and alcohols.
Couple of things. First of all, the graph on the left that you're seeing, indoor is red, outdoor is gray. Indoors, we have a lot more of these water-soluble gas concentrations than outdoors. This is important because water soluble is actually kind of a special thing. When you're talking about outdoor emissions, which is what most of these chemists who did these research experiments were coming from, is researching outdoors, they were all really shocked because you don't get a lot of water soluble gases emitted outside unless they get oxidized, which is something that the sun does and also something that ozone does and hydroxyl radical and other radicals that might oxidize chemicals. They can transform these into water soluble, and then the rain is able to come down and wash those away, which is kind of part of the cleaning process of outdoors. On the right, you see this mass balance that she mentioned. And again, this is for water soluble organic concentrations. Again, we have a big bunch of white at the top, which I was like, what's that? So just like most of things in life, you can't see something like you won't recognize it unless you know exactly what you're looking for. And unfortunately, there are so many chemical compounds around us all the time. Just as a quick, if you're like just dropping into this after not having seen any of the home chem experiment videos, which there are dozens and dozens of, probably over 60 at this point on our channel, or having seen Home Diagnosis, you might be in over your head at this point. So feel free to know that there are 101 level courses over there. So these unknowns, though, are the chemicals that are floating around our faces all day long. And this is gases. Remember, gases are things that are specifically in the air. around us. So the fact that they're unknown is like, I just thought that was interesting. That's a huge bulk of it. The other thing is that a lot of these, acetone, ethanol, pentoic acid, you got what you mentioned before, which is acids and alcohols. And those happened to be from personal products, degradation of materials like building materials, and all of the things that are on this list are actually very common, which is why they are the things that are known, and then they just didn't know what else they were looking for with the unknown. By the way, one other thing I want to mention on this graph on the left, you notice the variability between the red bars. That means that some of these houses had twice as many water-soluble gas concentrations as others. And that she was, kind of like positing that maybe it's based on behavior. It's either more emissions, more sources of them, or more sinks for them, more places for those compounds to get sequestered and kind of what's called partitioning, which you're going to hear about in a minute, partitioning onto surfaces. So it's not necessarily that those houses are cleaner. They might actually have more surface areas. If you imagine like an Applebee's versus a Swedish, minimalist restaurant. Okay, let's continue.
Ammonia is another water-soluble gas, and this is work from Peter DiCarlo's group, and it shows a frequency distribution for ammonia in home chem campaign. And also the symbols here are from the literature for concentrations indoors at schools and offices and homes. And you can see that those concentrations are much larger in general than the concentrations found outdoors, which are generally below this dashed line.
Okay. So this graph blew my, like, I did not understand any of what she just said when first time I saw this, or the third time I saw it. When she explained it to me, so first of all, you've got two graphs in one on this. That's why it's a little bit weird. So first, the high outdoor is the dotted line that's at the left. That is parts per billion of NH3, which is ammonia. So ammonia, which she's going to also name NH3 later, it'll come back, is maxes out at the very, very low end, like around 10 parts per billion outdoors. That's a high level. When we start measuring indoors, the first thing we find is that, like, we're blasting past the outdoor level entirely. Outdoors has nothing to do with indoors when it comes to this ammonia concentration. What you see on the homes is just from the homes that were researched in North Carolina. So this is like a batch of homes. You can see that one of the homes happened to, in summertime, that's X right over here, happens to be below the highest outdoor concentration. That sounds like, oh, maybe a healthy home. But then you see every other single one is above that. And they tend in wintertime to be higher than in summertime, right? So you've got the O's, which are winter over here. You get the X's being heavy on this end. That's these 13 homes. And that was one point in time measurements. This orange line here, this line graph that's laid over the background, is the home chem campaign over weeks and weeks. So it was a 4-week campaign, and they did it in this one house in Austin, Texas, at the University of Texas. And this was the number of test samples that they took, how many times, the frequency that they got these readings. So what you see is there's kind of a bell curve here where, like, most of the readings tended towards this kind of middle, like around 30 parts per billion. And it also looks like if you took out of time, not time-based, but just one sample in time, you'd see the kind of same bell curve distribution. So I thought that was kind of interesting. The other thing is that offices, they measured an office here at the lowest end of the homes. They measured an office here at the highest end of the homes. By the way, the triangle means they don't know when the sample was taken. But then we skip from 80 to 100, so we don't have to make this thing super long. And it goes 100 to 280 to 460. And they found concentrations in offices and in schools way beyond what we found in homes. So just like, this is an interesting exploration, I think, because we're putting people that don't have any control over their environment, not just into rentals, but also into schools and into office buildings. And these are places where, like, it's pretty polluted. And also it means other things for, like, the chemical reactions that can happen, which are also very important.
Ionic PFAS and polyfluoroalkyl substances also elevated in indoor air, and they are water-soluble compounds.
Okay. PFAS. So this is things that are going to let materials, it's kind of a miracle chemical, is what the people who make it and sell it want you to think about it as. Is really a horrible thing for our environment and a horrible thing for human health. These big companies that make these chemicals have spilled and polluted like just a ton of places. And this is bad news. So if you work at a chemical company, think about getting a different job. That's just my little advice because I think you're going to end up being on the wrong side of history. But all that to say, the PFAS is kind of unavoidable. Even if you don't live by one of these factories, your environment is polluted. They found it inside of polar bears, who don't live anywhere close to factories, obviously. So these come in a couple different flavors. They help stain resistance, help with water resistance, and they help with heat resistance. So she's going to kind of go on about this, but also the ionic thing. I asked, is all PFAS ionic or is it more dangerous than anionic? She said that there are PFAS that can be ionized, that are like acids. And then there are others that can't be ionizable, which have not been studied at all for health effects, basically. So the ionizable ones, they have studied for its health effect on humans. The non-ionizable, we just don't know what it does. So they're just kind of like just trying to look at what they know is important.
So this graph shows concentrations in 10 North Carolina homes. The top graph is indoors. The bottom is residential outdoors, and this little black bar is the regional outdoor concentration.
This little black bar is the regional outdoor concentration. So super low regionally. In the neighborhoods outdoors, outside of these homes, you get a lot higher just for the fact that you're in that neighborhood. And then indoors is way, way higher than that.
And so residential indoor concentrations are 2 to 3 times higher than the residential outdoor concentrations. And residential indoor concentrations are an order of magnitude higher than the regional background.
That means 10 times higher, an order of magnitude. Also, these things can also make things slippery too, and they used it in food takeout containers, incidentally. So these are just bad news, and they knew that they wanted to look at these because of the health impacts. By the way, these things at the bottom right, the greens and the blues and all that stuff, these are like all the different flavors of PFAS that they've got. The black there is the sigma of the PFAS. That means the combination of all of them. That's the regional. So they were looking at just like total. It's like total VOC.
The behavior of water soluble gases has a wide variety of implications. So here are a few of them. Some water soluble gases are toxic, like some PFAS compounds, for example, and their chemistry, their partitioning, their fate are important to understand because of their impact on exposure. And this probably includes not only inhalation exposure, but also dermal exposure. So this is illustrated in this figure here, which shows the gas phase concentrations of neutral PFAS in 10 or 11 homes in North Carolina. And this is Clara Eichler's work, and she talks about and measures partitioning of those gas phase compounds to clothing. Water soluble gases indoors also leave the house and go outdoors. And that can be important, for example, for compounds like volatile chemical products that are precursors for secondary organic aerosol formation.
Secondary organic aerosol formation means particles that were caused by chemistry. And chemistry, remember, is chemical reactions. It's like two things coming together and birthing a thing that wasn't there in the beginning. So secondary PM2.5 is their shorthand of just saying particles that originated from chemistry, not from little blobs and droplets of things sticking together. This is something that the sun can do. It's something that our chemical reactors that are based in our homes can do. By the way, just a little PSA, don't buy blue lights, don't buy ionizers for your home. Those are chemical reactors, and they can create these little secondary PM2.5. Oh, one other thing. Partitioning means chemicals moving from the gas phase in the air onto anything. It could be a surface, it could be into a building material, it could be onto a water droplet, it can be onto clothing, etc.
Compounds like ammonia partition to surfaces in a large way and can then release other bases, for example, nicotine. And those surfaces can then take up more organic acids.
Okay, so let's talk about this ammonia going to and from the surface over here. We've got this little figure right here. So they did an experiment as part of the CASA campaign, which is inside of Home Diagnosis Season 3. You will see more on that because we got some footage from it. It's honestly like so much stuff that I have, since I edit all of our videos, I have a hard time getting back to that stuff sometimes. So the thing that they were trying to measure is the pH of homes, because nobody's really tried to measure this before. And it turns out it's really important because you measure the pH of pools, you measure the pH of soils. Nobody's doing it in homes. So what they found is ammonia is a base. And then, so they used ammonia, they introduced ammonia into the air. And of course, because of this partitioning thing where the ammonia then would go onto surfaces, it's kind of like magnetism. What it will do, if you put a plus sign from a magnet, all the other plus signs try to run away, and it will attract the negative, which would be the acids in this equation. So when you put ammonia onto surfaces, a lot of the other bases that were on that surface will jump off into the air. And then they can measure them with their little instruments that are just right there ready to capture all this stuff. And that's how they can measure how many bases are on the surfaces, is by forcing more bases onto the surface, seeing what jumps off.
And inorganic acids, nitric acid, for example. And water-soluble gas behavior depends on surface-associated water and on building operation.
Okay. And this is the thing that's like so important, that we're putting this information on our channel. I feel like that's the only thing she's going to say about building operation. She mentioned it. I think that this is critically important for people to understand, because what the conversation mostly has been among the nerds in building science is about dew point. We talk about surface temperatures and condensation. We're worried about that. We talk about heat bleed. We talk about vapor diffusion, if you want to get super nerdy, and you talk about, thermal bridging and things like that. And this conversation about water films is like a real sideline. You might hear Joe Seabrook talk about it as a moment in one of his talks, but like there's not a lot of talk about this, and they don't, and it's partly because they haven't learned a lot about it until recently. So building operation means heating and cooling, means the amount of insulation, means the amount of air tightness you've got, means the 5 factors of ventilation: circulation, capture and filtration, humidity control, dilution air, and pressure relief. Okay, all that stuff is that is what she's talking about. And of course, we have hundreds of videos on that topic here, so you don't have to learn more from the chemists. That's kind of what our specialty is, our channel and other channels like ours on YouTube.
So there's quite a bit of evidence, actually, that there's sufficient surface-associated water to alter the fate of water-soluble gases. So here's a little bit of evidence here. Mark Webb, who's here today also, did some parallel plate flow reactor studies. So he used clean glass and authentically soiled glass. So these are pieces of glass that sat on the walls of people's homes for about 2 years, actually, and the chemical ionization mass spec. And he measured the uptake to that glass of organic peroxides. So,
okay. This bears some explaining, because I thought it was pretty fascinating. So Mark Webb, also in the show, awesome guy. Isoprene is one of the things that he was measuring here. Isoprene is biogenic. It means it is emitted by living beings. It's emitted by animals and plants, meaning us also. So if you see it, it's because there are animals and plants nearby. Okay, so that's just interesting. So isopoo is a what do we call it? An organic peroxide, and it is an oxidation product of isoprene. So when you have isopoo present, it's because isoprene was there and it transformed into this other thing. Okay, so there's that. The other thing that she's getting at here is that this grime on these authentically soiled glass panels is enough to uptake a ton of water. and she's about to get into the details, but basically clean glass has very, very little water film on it. It has, when it's soiled, then it gets like a lot
To that
more
glass
interesting.
of organic peroxides. So he used isopoo and isoprene derived peroxide as a model organic peroxide. And the graph all the way on the right here shows the uptake of isopoo to the clean glass at different relative humidity values, low to high. And there isn't that much difference. But when this glass becomes soiled in homes, at high relative humidity, quite a bit more organic peroxide is taken up by the glass than at low relative humidity. And you can also see that over here, that high relative humidity on soiled glass collects a lot more organic peroxide than low. And so this really suggests that hygroscopic species in that soiling, and RH, of course, lead to greater surface associated water and greater uptake of these water soluble gases.
So clean your homes. Just like Jason Earl said within one of the episodes, clean and dry, not just dry, also clean.
Another example of how surface associated water is sufficient to alter the fate of water soluble gases is illustrated by these acid-base experiments that Mark and Glenn conducted at Cossack Field Campaign. So there were SF6 injections that they used to characterize the airflow in the house and model that airflow in the house. And then ammonia injections, 3 injections of ammonia, the same amount of ammonia on a 70% RH day, and 2 injections at a 40% RH day.
Okay, let's pause for a second. SF6 is what's called a tracer gas. It's used because it's not supposed to be there. You'll almost never find it in real life. So if it's there, it's because you put it there. So if you put enough, like a known quantity of it into a home, I have a video on tracer gas testing because I heard about it and I didn't understand what it was. And finally, Attila, who's coming up later in this series, explained it to me. So SF6 is injected, a known quantity, just like they're doing here. In the case of ammonia, they've got, you know, the on the dry day and on the wet day. And the thing about SF6 is that it is not like ammonia in that it is not a water-soluble organic, and it's also not reactive. So it acts a little bit differently.
And then they did a little modeling, compartment modeling, and by using the SF6 to get the flow balance, they were able to get a really good reproduction of the concentrations of SF6 in the main house in the first and second floor and in the basement.
And by the way, the reason they look different is that they injected these concentrations into the upper levels and then it diffused. So you see the spike there on the main house. That's because that's where it was being introduced directly. Then it just kind of traveled down to the basement.
And then they applied that same model to the ammonia, and it doesn't work very well. So on the left here, this is the high relative humidity day, and the orange is the measurements of ammonia, and this is the low relative humidity day. So you can see in the measurements that there's less ammonia in the air on the high relative humidity day than in the low relative humidity day. And that's not reflected in the model. So to fix the model, they added surface reservoirs.
Okay, so before we move on to the surface reservoirs, just to be clear, the green that you see at the top, that is what's supposed to happen based on the model. This is why modeling is like, it's so useful to us in this field because you want to predict what's going to happen in the future without actually doing it, but they have not trued this model up because it's the first time that they ever did it. So it's supposed to spike way up and it didn't. It hid way down low. That's the gold line that you see on the wet and the dry days. And that is, she's going to get to in a second, the specifics on this. But basically what that means is that it's not in the air, not because it's not there, it's in the surfaces. So it almost immediately then found its way into these surfaces to the tune of the rest of what would have been there. So it would have matched the green if surfaces weren't there.
And they actually found that after that, at the 24-hour mark, about 80% of the ammonia was in the surface that they had injected was in the surface reservoirs. So this is their best fit model with the reversible surface reservoirs included. You know, the peaks don't exactly fit, but it does reproduce the shape well and the rise well. And it reproduces this, this feature where you have lower ammonia concentrations on the high relative humidity day than on the low relative humidity day. And the reason I show this plot is to tell you that the best agreement for this model was found when the surface reservoirs at high relative humidity are 50% greater than those at low relative humidity. So it provides some evidence that the surface associated water was really important for ammonia uptake.
Okay, sorry, I'm still getting slick with the pausing. I'll get better as the series continues. What this means is that between a 40% RH day and a 70% RH day, they found 50% more of the water-soluble organic compounds held in the surfaces. So an extra half, again, was taken up with only a 30% rise in relative humidity. And like, again, just to reiterate, we're always worried about this 100% humidity, this dew point. That is not what she's talking about. She's talking about very reasonable. 40 to 70 is like normal homes that are not high performance. My home sits right at 45 if I want it to, because I've got all the equipment and the air tightness and all that stuff. But normal homes do that. And that means that 80% of the chemicals that were injected into the air get pulled into the surfaces to be re-released later. By the way, this is something that lead, I'm talking with, there's a guy on Instagram named Eric, who's got like Eric Everything Lead, I think is his handle. And so I'm doing an interview with him coming up soon. And they were just doing some research and found that if you are exposed to lead, it finds its way into your bones. And it sequesters there, partitions, basically like what Barb is talking about here. And then later, as your bones deteriorate when you get old, the lead comes back out and hurts your brain all over again. Isn't that crazy? So a little side note, but I just thought that was interesting. We're going to be like testing for some lead. I've got a little test kit over there.
The importance of water is also shown, and I think a lot of people have seen this plot before, but it's also shown with the uptake to HVAC systems. And so this shows a plot by Sarah Duncan. We had a chemical ionization mass spec in a home in North Carolina. And every time the peaks of acetic and formic acid drop is when the AC system kicks on. And so you can see these water soluble gases being taken up by the air conditioning system, probably because of water in the AC ducts and the AC condensate.
Okay, super interesting. So first thing I asked her is, okay, so you can see these spikes go up, go down, go up, go down. Every time it goes down, the air conditioner coil got wet enough to form condensate. This doesn't happen in all homes, by the way. So if you have an air conditioner, it doesn't mean that this is happening. It has to run for at least 10 minutes to get wet, at which point it's pulling out these gases. So when that happens, that's nice. If we could have that happen as long as possible, that's better. That's a better sink. It's an extra filter for your home that you do not have built into your home, because filters for HVAC, even if they're HEPA filter, don't pull water soluble organic gases. You need water to do that. And so your AC coil becomes at that point a filter that literally throws itself away. You don't have to like change this filter or anything. I think that's beautiful. If you have a properly sized air conditioner, and all my HVAC design professionals, all my HVAC installers, listen closely. If you have appropriately sized cooling that is going to run and is going to cool as long as possible and keep that coil nice and cold and wet, this graph looks very different. It's just down. It's down, 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 down. right? And then every time the thing turns off, it'll jump right back up, which we'll get more into in other sessions as well, and was already mentioned. But so this, I think, is very important. It is technically building operation. Most people don't actually control how their homes do this. Mostly it's air leakage, insulation. It's mostly air leakage, insulation, your window types, all that stuff. So this can be very important, but remember that your HVAC is becoming an important player in this conversation about the control of these gases. Oh, and by the way, one other thing, acetic acid. Acetic acid is vinegar, basically. Interesting. Formic acid, let's see here. Lactic acid, I don't know. Formic acid, I think, is just another common acid. Lactic acid was really interesting. That's people. And it's also cooking meat. So those two things are what the lactic acid is coming from in this graph.
Ducts and the AC condensate. Peter DiCarlo's group has also shown this for ammonia. So you can see ammonia dropping every time the air conditioner comes on. So in conclusions, I'd like you to come away knowing that water-soluble gases are abundant indoors, that surface-associated water is present in sufficient quantities to affect the fate of water-soluble gases at higher but relevant indoor relative humidity levels.
And by the way, that means over 60% when she says that. So she's talking about anything past 60%, which is very common in homes that are not well controlled for performance.
And that's because of the large surface area to volume ratio and the hygroscopicity of surfaces and materials in the indoor environment. There are many potential implications of this. One of them, if I think about all the ammonia that's in the surface reservoirs, is that when PM 2.5 comes in from outdoors, and especially on the West Coast, there's a lot of nitrate in PM 2.5. And the nitric acid in indoor air gets sucked up by the ammonia in the surface reservoirs, and it pulls nitrate out of PM 2.5. And so it alters people's exposure to outdoor generated PM 2.5 when they breathe it from the indoor environment. Another one is the partitioning and exposure of toxics, for example, PFAS, through clothing. And then, of course, there's increased indoor residence times for water-soluble gases because of their association with surfaces. And that provides more time for chemical transformations that could subsequently alter both indoor and outdoor air quality.
So again, because the chemicals come into your home and then they just set up camp there on a surface, they'll come off every now and then, but they might glom onto another surface or onto you or into you, etc. It provides that time for these chemical reactions for those things to then birth other things that weren't there to begin with.
So in conclusions, I'd like to thank the Sloan Foundation for funding the bulk of this work. And some of this was supported by traineeships from NIOSH and from NSF. Thank you.